actually through
Recording in
vector addition.
progress.
So VB, and this is something we did last time, right? We just didn't do the bearings. So our still water velocity plus our current is going to equal our true velocity. And what we want to get the true speed and bearing, this is the magnitude and angle of our vector V, okay? So we're given a few things here. We know, let's fill in what we know, and then we can kind of calculate, right? So we know that we're set to travel 10 knots, right? So we know that the magnitude of our VB, like in still water, is going to be 10 because we want to travel that 10 knots. And then we also want to figure out the angle. So they gave us this as well. So the blue that I like colored in this picture, right, is just the 25, but we want the angle, our theta is going to be starting from 0. So our theta is actually going to be this entire thing, at least for now here, right? And that's 115. So we have our theta is 115 degrees, and they just did 90 plus 25, right? That's how we got that. And so we now, I mean, ultimately, we want to do this, right? So what we need to do is we need to say, okay, VB, this vector, is going to equal, and we're going to use that formula A cosine theta and B sine theta in order to find our actual vector form, our component form here, right? So A, I mean, this is A, so it's going to be 10 cosine 115 degrees, and then 10 sine 115 degrees in this component vector, right? And then the current, so we'll calculate that, or let's do that. And I did round this, even though we use it again later. So I don't know, in your homework, I recommend probably don't round until the end type of a deal, right? If you're having trouble, that's what I would guess. But I did round these 10 cosine 115 about negative 4.2, right? And 10 sine of 115 about 9.2, no, 9.1. And so now we want to get this one. So now we want to get, we have VB, add VC, and that's how we'll get this magnitude or this vector via our true velocity. And then we can, and then we'll get the speed and direction or the bearings, right? So VC is going to be, what did they tell us the current? They told us, oh, it's due west at 3 knots. So that just means if we're looking, north, south, east, west, it's due just west. Like, no, I mean, you can look here, right? It's a straight line just due west. There's no in south about it. And it's 3 knots. So if I, put a point right here, it would mean if I look at this as an X and Y type of like axes thing, the components, it's -3 in the X and 0 in the Y, right? So it would be -3, 0. And you could just say that A is 3 and B is 0. Or no, I'm sorry. You could say that A is 3 and then theta. So another way to find this, if you weren't really sure, your A is 3 because they give you this 3 knots, but your theta, look at what direction west is. Your theta is 180 degrees. And so if you do this, you get 3 cosine 180, which is just -1. So you get -3 times 1. So or -1 times 3, right? And then you get 3 sine of 180, which sine is 0. So you get 0. So this is how I also computed that. If you're wondering, like, how the heck do you figure that out, right? Okay. So now that I have these 2 vectors, I can take, this and this and add them to get my vector V. So I'm going to say V is going to equal negative 4.2 comma 9.1 plus negative 3, 0, right? And we know we can just add these component wise. So negative 4.2 really minus 3 and 9.1 plus 0. So, oh geez, what did that give me? Negative 7.2 and 9.1. Oh, running out of space there. And so this is my velocity vector. It's the true velocity. But I want magnitude and the angle, which is the bearing. And so I know my formulas, right? So to get magnitude of V, I just do the square root of each component squared, right? So the square root of negative 7.2 squared plus 9.1 squared, right? And this here will get us the true speed. And I'm getting, and this is where you round to 1 decimal. So again, maybe you don't want to round before this, but if you did, you know, I don't know if that's going to affect on the mark, but I'm getting about 11.6 knots. And actually, the way that I would figure this out, if you need to round or not, like earlier at the end, is look at that, like hit the similar example or the help button, right? And see what they, because you'll see right away, like if they round at the beginning in their work, or if they round not until the very end, you'll know it should help you with the homework. So now I use another formula. I have, you know, tangent theta is my components B over A. So 9.1 over negative 7.2. Now, keep in mind, when I do inverse tangent here, if I don't get, we're looking for an angle between, we're looking for an angle, well, okay, look at the picture. We're looking for an angle that's really between like 90 and 180. It should be here because this is where the direction of our vector. So if for some reason we get like the opposite one, right, or something like that, we just might have to add or subtract 180 or 90 or something to figure out what is this actual angle. So let's see what we get. And we might get the right answer like this. So I'm saying this because it's not always the case that you have to like change angle. If we did inverse tangent and we just got, 100 degrees or so, I don't know, then we would say, oh, this, this is north one. Well, okay, then you'd figure out whatever 100, it's 10, but so that's totally not right. But you'd figure out what this angle is from the north part, and you'd say, oh, this is north 10 degrees west, right? So let's just check this out and see what we get. So I'm going to say theta is inverse tangent of 9.1, well, negative over 7.2, right? And I get, well, approximately negative 51.6. Okay, so what this means in degrees, I'm in degrees here. So what this means is that, okay, my angle is negative. It's from, because the angle I'm solving for is from here. It's from the x-axis that I just, the 51, negative 51.6. So that's, okay, like here, I don't know. And so this would be like 51.6 degrees, and well, technically negative, right? And so in order to figure out, oh, what does that mean for this guy here, right? Then what I have to do is I have to say, so I want to know this angle. Oh, maybe I should do a different color. Hold on. So basically, I'll start by like, this is the vector here, and the angle that we found is equal to this. So this right here is 51.6 because they're vertical. This picture is okay. I mean, obviously still not drawn to scale, but they're vertical angles here. So this angle here is also 51.6 degrees, just like the angle formed by the blue and the yellow lines there. And so if we want, maybe I'll do this. If what we want is, we want from the north and then from our new V vector. So we want this dark green angle, and we want to know what is that. So to get that, so we're interested in this, maybe I'll call it like alpha, right? So to alpha, we're going to do 90 degrees minus 51.6. And that's just because, there's different ways you could have calculated this, right? But this is how, this is kind of the pictorial way maybe that you would calculate this. And so that's going to be about 38.4 degrees. And what that means is true. So here was my true speed and my true bearing. It's just the angle measure, right? But keep in mind, what direction am I going? So look, this big thing here was my vector V. And so I was going north 38.4 degrees west. And that's my true bearing. And we wouldn't say 51.6. Like technically, if you something like, west 51.6 degrees north, then that's telling me that you're going west, and then 51.6, which is this angle here, degrees north. That's the same thing, but we just typically, and what is like just typically done is we always start from that north-south line. So that's why we start with north-south. That's why we have to maybe subtract from 90 or 180 or do a little, have a little picture here. Where does 11.6 knots come from? 11.6 was this right here. And this is the magnitude of the velocity vector. And the equation for that was just, so if your vector equals like A comma B, the components, the magnitude of that is just the square root of A squared plus B squared. This has to do again with Pythagorean theorem, right? Because technically the magnitude of that is like the hypotenuse, and we're solving for the hypotenuse. So hopefully that made sense.
So the current is making the boat go like a little bit faster and a little bit more to the west.
Right. Like the current is actually, helping the boat maybe move along, but it's pushing it. So the boat, like if they wanted to go straight or something, they'd have to steer, or maybe if they didn't want to be pushed so far west, they would have had to steer in the opposite direction and continue, right? And then it would push them exactly where they want to be. So that is something that people calculate. And then that picture that we saw before,
that was similar to that other one.
Yeah, it was actually really similar to this. It was, oh my goodness.
You went past it, but okay. Like if you want to go straight up, then you have to like subtract it.
Right. So if you want to try to avoid the rocks, right? You, based on the current, how it's moving, you need to kind of decide this. And there's like machines and different things that actually calculate like currents and help people show if it's changing, so that if you are steering like a large boat, so you're not going to crash into something, right? So that's actually what they are doing. Granted, okay, I cannot drive, but I do know that exists, and that's kind of how people can, in heavy currents, like that's how you can maneuver your boat in like the right direction, I guess.
Cool.
Yeah. And you are required to have a boating license. If you're like riding a boat anywhere, you need a boat license. I just know my parents have done that. That is why I know. But okay, so now we're moving on to 8.5. So hopefully, if that was the little tail into 8.4 that we didn't get to, but we have dot product here. Okay, David, you're so right, but I didn't say it. You didn't say that. We know, right? Let's just hope you don't get in an accident. That's all. But yes, so our motivation here is this problem. Let's take a look. A third-year student takes courses to make up a full academic load for one semester at ACC and UT, with 6 hours at ACC and 9 hours at UT. Wow, that sounds extremely stressful. Each hour at ACC costs $85, and each hour at UT costs $750. Makes sense. This is why community college is amazing. And I wish I did save a little money and start there first, but here is okay. But it is smart of people that do well. If you are, that's what you're doing, that's great. And what is the total semester tuition? So, okay, this is something that actually potentially could to you guys, and you could be calculating, right? I don't know how true to the actual, or I don't know how true this is to what prices are actually, but let's see. So we'd have
but this person
ACC.
must not work. That's all I know.
Yeah, okay. So we have ACC and UT, and ACC, they told us 6 credit hours with $85 each. So 6 times 85, right? That's what we're doing. Then we'd want to add, if we want to see what's our total cost, then we have 9 credit hours at $750 a pop, right? That's, sounds brutal. I mean, UT, great school, I'm not knocking it, just saying. And our total is going to be here, and that's going to be whatever this is, 6 times 85 plus 9 times 750, like $7,260 just for, and this is just for tuition. So, I mean, I guess maybe that's realistic. I don't know, right? Maybe it is 5 years ago. Okay. And notice here that this is just a number, or scalar is how we called it before, is not a vector because it only gives us a cost, right? It's not a vector. But we could say, if we wanted to make this, I mean, okay, this is a simple problem that we can just calculate without using vectors. So that's a little silly, but this is one way. If I said, what are my hours? So let hours equal the vector 8. Well, my hours in a vector would be 6 and 9 because it was 6 at ACC, 9 at UT. I almost said St. Ned's, but teach clear, that's probably why. Then we have tuition, and let's call that vector T. And this was 85 per credit and 750 per credit or credit hour or whatever, right? And so you can see, 6, 6, and 85, or maybe we're here, right? The 6 and the 85 are there, but then you see the 9 and the 750 are in these components. So what we actually just did here, I mean, this is our motivation, and maybe we'll come back. I won't, well, maybe I've already given it away, but maybe not. So here is like the grand finale of what we get. If you have a vector, A1, B1, V, and a W vector, A2, B2, the dot product is V dot, and it's actually just addition. It's basically, multiplication of each component and then addition. So notice what's happening here, and maybe I'll do this. So I'm taking V dot W, so this dot product, and I take the first component A1 from V, then I take the first component A2 from W, multiply them, right? Then I add, and I do the same thing again with my second component of V and second component of W. So this is the dot product. And what's happening is we're taking 2 vectors, we're multiplying them together, and we actually get a scalar, right? We change from vector to scalar. So that's what this says here. The dot product results in a scalar, not a vector. It's kind of like the magnitude of a vector results in a scalar, right? Because we do the square root of each thing squared and we get the magnitude, right? So let's practice. So number 2 says.
So if you calculate their magnitudes, do you get the same thing?
Okay.
If you add their, you know what I mean? If you calculate the magnitude.
Yeah, and that's a good question, but no. So the magnitude, well, I see. If you do the magnitude of each, it's still a little different because that equation is just different. Right. Because we're squaring each component and then taking the square root and adding. So it's just a little bit different.
It's not the same thing because you leave out the, that's interesting.
Yeah. So yeah, I mean, and maybe along the lines, maybe we'll figure out that it is the same, but you'll see. Okay. So I see it later on. We're going to get to that. It is related, but the magnitude is not equal to the dot product. So well, it is related though. So we will see this. So first these examples, if I just have v dot w, right? Then I have -2, and you can write it like, well, so I'm writing dot 314. You don't have to rewrite this, but okay. So this is just -2 times 3 plus 2 times 14. Okay, so -6 plus, what is this, 28? Okay, mental math, it's hard. Okay, so this is just 22, okay? V dot V, okay, kind of weird, but this would be, and again, you don't need to write each of these, but I'm just trying to be very clear with what we're doing. So this would be -2 times -2 plus 2 times 2. Okay, seems that's a lot of twos. Terrible twos. There you go. So -2 times -2 is 4, and then 4 again. So this was just 8. And then W times W be less twos, thank God. So that's great. And we can write it like this. And we'd say this is 3 times 3. Now keep in mind, plus 14 times 14. This looks awfully similar to, this is what Michael was talking about. This is 3 squared plus 14 squared. That looks a lot like what we do for the magnitude, right? But notice how this is why I was struggling thinking about it before. We were multiplying V times V dot product with U, but here we're doing WW and VV, right? So when we do the same, it's exactly like the magnitude, but not taking the square root. So you'll see what we do, and let's figure this out. I think, okay, 9, I think it's 200, 205. Yeah.
It's like the magnitude squared.
Exactly. So if you look down at these properties, so this is where we're just hopefully learning, and the brain is turning, you know, the dogs are barking, it's a good time. So now these are just, so right here, they're just properties. They're not, you know, don't, I'll have to see. I really need to figure out what you need to memorize for this test next week. I'm dropping the ball on you guys, but I want to say you'll be given most of the properties, but the ones that are, except for the ones that are kind of obvious. So like this first one, it's the commutative property. V product dot W is W dot V. They're the same thing. And it's because addition and multiplication are commutative. Same thing if we have a constant. So actually, so maybe I won't give you these, but these are just things to know, right? So if you have a constant, I'll write what these are. This is the commutative property. This is actually the associative with a scalar, like C is just, it's like the number 2 or 5 or -1. So associative with scalar multiplication. Okay, I really can't spell. Multiplication. Okay. Then we have this next one, which hopefully you do recognize, is the distributive. So if I'm doing V with a dot product of 2 vectors that are added together, the distributive property holds. And it's the same thing as doing V dot W plus V dot U, right? And maybe something is like maybe one way is easier than the other. This is why it's good to know, even for these, maybe it's easier to multiply the C first, or maybe it's easier to do the dot product and then multiply the scalar. So these properties are just reminding you that you can do these different ways, right? And then notice exactly what Michael was talking about right up here relates directly to this guy here, right? So can you take them out? So like V with the dot product V is the magnitude of V squared, right? So that is a very special property. And then this next one, I mean, I'm not going to say, I guess, boring, but maybe kind of boring, that 0 dot product, like so this is, this right here is the 0 vector. So like however many zeros, so what that means is, so if V is A comma B, or okay, right, then the 0 vector dot v actually equals 0, 0. Like there's just a 0 in place of every component that you have. Okay. And that's why it's 0, because 0 times everything is 0. If I add 0 a million times, it's 0, right? And then the last one is a combination of everything, one pretty much. So let's, well, so these, if we take 1, 2, and 3. Well, I think it's the first 3 pretty much. Kind of, maybe it's just 1 and 2. Oh shoot, maybe it's just 1 and 2. All right, hold on. It's just 1 and 2. Let's go with that. Okay, so this is the commutative and associative combined. So these are just properties that we may use, you may see, and you should just be aware of. So actually, and now that I look at them, they aren't like actual equations you have to memorize or anything. So this will not. So, okay, now I'm happy that I realized that. I was a little bit worried, like more equations you have to memorize, but they're not something that, you know, you'd be tested on. Like as long as you know what the dot product is, you can do these things without thinking you're wrong, right? Basically. And it's, I think, a little bit intuitive, right? Like if the dot product is just multiplication and addition, it should hold the same properties as multiplication and addition, and it does. Okay. So now we take a look, we have angles between, or angle between two vectors. So maybe we have a vector v, and suppose vector v, there's this angle alpha, right? Then we have a vector w, but w, the angle is actually, you know, this whole big thing here to get to w, maybe call that beta. Or, no, I guess we won't. We'll call this, no, yeah, we will. Let's call it beta. Okay, we'll call this beta. Then what you want to find typically is, if you're dealing with these two vectors, is the angle between the vectors. You don't really care what the angle of the vector is from like 0, from the x-axis, because maybe you're, you know, computing something just with these two vectors, or trying to add them together, or find the distance between them, something, right? So what we care about is theta, and notice that theta is just beta minus alpha, right? Hopefully we see that, okay? And why? Why do we want the angle between two vectors? Where is this helpful? Like, why are we using any of these, alpha, beta, anything? Well, if we get vector v, we'll start, or maybe I'll keep these in maybe colors. So if we have vector v, and we get, it's the magnitude of v times cosine of alpha. I'm using that formula, but using, but instead of saying a cosine beta, I'm using what it actually would be. So the magnitude times sine of alpha, right? Then we'd have w, which w would be the magnitude of w, and this is the component vector, cosine of beta, the magnitude of w, sine of beta. And so if I was doing the dot product here of these two vectors, and this is very, very general. So if you're a little lost there, it's not a specific example. It will be easier when we have actual numbers to plug in, right? So do not fret, it will get better. But if we wanted to do v dot product w, we can say, well, this is just, remember, the equation is the first component times each other plus the second component times each other. So I'm going to write it exactly like that. So I'm going to say it's the magnitude of v cosine alpha times the magnitude of w cosine beta plus the magnitude of v sine alpha, the magnitude of w sine beta. And what's happening here is we can factor out. So each of these, notice each of these has the magnitude of V and magnitude of W. So we can factor those out, right? So we can factor out, okay, let me write that. So we can say this is equal to the magnitude of V times the magnitude of W. And remember, the magnitude, these are just, okay, maybe I should have, these are scalars. These are just numbers. So it's a number times a number. It's just a number, right? It's Y or it's P or something. It's just a number. And then times what's left over, cosine alpha, cosine beta, plus sine alpha, sine beta. Now you may not remember this, but this looks awfully familiar to something we did a long time ago, right? With sum and difference of sine and cosine formulas. Now, if you don't remember which one it is, that is okay. But when I have cosine, sine, sine, and it's plus, I know cosine, what I'm looking at, and it's the opposite of this sign. So it's going to be angle subtracted. So check this out. We are going to have the magnitude of V times the magnitude of W times well, maybe I shouldn't do it, times cosine of beta minus alpha. And notice I so maybe cleverly did here. Beta minus alpha, what is that equal to? Theta. Okay. And I did all of this just to show you because, or just to explain to you, you do not have to know, all of this or for a test or anything, but this is the explanation. And again, why pre-list about this is hard, right? Because we're doing all the background. We're learning why this is true and the reason for it. But then when we apply it, you don't actually have to use those reasons, but pre is about learning that and knowing those reasons. So what we see here is the dot product of V and W is also, so you could do that whole A1, A2 plus B1, B2, but let's say you don't know the components. You don't know A and B or A1 and B1. You don't know the components. So what you can do is you can just multiply their magnitudes and then cosine of theta, the angle in between them, right? Oh, really? Okay. Okay. So, and keep in mind, in this case, we do want to keep theta between 0 and 180. This is just where it's kind of like when you have sine and cosine. Well, when you have sine and cosine, you want certain tangent, you have certain domains for getting inverses and things. Well, in this case, typically, if we have an angle, right, or if we have two vectors, we don't want if a vector this way, but then I don't know, I'm trying to think like exactly this way, this angle between them is 180. If it's any other, if it was like a little bit this way, I would not look at this large angle. I would look at the smaller angle between them, if this makes sense. So I would look at this one, right? So our angles, no matter what two vectors you have, the angles will always be between 0 and 180, or that's the ones we will use, right? And that's actually what this next picture, I guess, shows. Maybe I shouldn't have drawn it myself, but orientation does not matter. So looking at, we could move V and W around. So like, look at this, W is going this way, V is going this way, and here's my theta. That's one picture, but I could take W, reflect it to go this way. So now here's W, take V, move it up a little, or maybe they didn't move it at all. I don't, maybe it's a different problem. And here's theta. So these two examples, you should get like this, whatever this theta is here, as long as V and W are the same vectors and they're just shifted, scaled, or moved around, the angle between them is going to stay the same. Okay. And we will always use the positive angle not negative. So if you get a negative angle, you want to just figure out, okay, do I just take absolute value, or maybe do I subtract it like from 180 or something like that? Like, what angle am I getting? So it helps to see your picture. So like, if looking at this, we would never use the angle going necessarily in that direction, because that would be negative. We'll always use the angle going in this direction, even though W is down, like maybe we're doing V dot W. That doesn't matter, that W is below the angle. We just want the positive angle between these two. That's between 0 and 180. And something to note in this picture is that if I go from V all the way to W here, we never go the long way. This would be the long way, right? So we never go all the way around. We want that shorter. There's always going to be, no matter what two vectors you have, there's always going to be one angle that's between 0 and 180 and the other way that's way longer, right? We want that shorter angle. So now we're looking at find the exact. So now we're back to exact because they're giving us theta is 45, right? So because we know how to compute sine and cosine of 45, or really just cosine in this case, we want the exact answer. So, and they give us everything we need. So V dot W is going to equal magnitude of V times the magnitude of W times cosine of the angle in between. So they gave us everything here. So picture doesn't even really matter, right? They said that's 5 times 7 times cosine of 45 degrees. And so that's 35 cosine of 45 degrees, which is, what's that, root 2 over 2, right? So 35 times root 2 over 2. Can't really simplify that anymore, so because 35 over 2 doesn't reduce. So we'll just leave our answer like this. And then number 4 is saying find the angle. So now we're going to be finding the angle. Keep in mind, again, it's got to be between 0 and 180. So if we get this, great. If we don't, just remember you have to maybe do a little bit of math or draw a picture. And they give us these vectors. So this is a little bit, they give us V is negative 2i plus 3j, W is 3i plus 4j. Remember, all that means is that V is negative 2, 3, if you like it this way better, right? And W is 3, 4, right? So it doesn't matter, and we want to round to the nearest 10th of a degree, okay? So I'm going to write the equation again, V dot W, and you don't need to keep writing this, but I do think if you write it, the more times you write it, you're just going to have this memorized, right? So this is what the equation we have. And in this problem, this is what we need to find. They're giving us the rest. In the other problem, we had to find V dot W, but in this problem, we want to find the angle between, so theta, right? So to do that, I'm going to start by getting the magnitudes. I mean, we have V and W, so I want to get, or you could start by getting the dot product, I suppose, but I'm going to get the magnitude of V is square root, right, of negative 2 squared, which is 4, plus 3 squared, which is 9. So the square root of 13. And then the magnitude of W is the square root of 3 squared plus 4 squared. So 16 and 9. So square root of 25. Ooh, that one's nice for us. It's just 5, right? And then V dot W, we can also calculate by using these component vectors here, right? So I'm just going to know it's negative 2 times 3 plus 3 times 4. Right? And let's see, what is that? Negative 6, 12. Okay, so just 6. Okay. So now what do I have? So I'm just going to set 6 is going to equal square root of 13 times 5 times the cosine of theta, which means I'll start by dividing both sides by square root of 13 times 5, divide by square root of 13 times 5. And maybe I won't rationalize here just because we're putting this in the calculator anyway. So I get cosine theta, or it's here. I get cosine theta is 6 over, well, I'll write 5 square root 13. And so theta is going to be the inverse cosine of 6 over 5 root 13. So you can just enter that right into the calculator and make sure you're in degree mode and get what that is. If you were hungry. Yeah. I didn't make one, but okay, sorry guys. Okay, so the angle here, give you 5 seconds to plug that all in your calculator. The angle here is 76. And again, you can, I mean, if it's too much for you to check right now, feel free to check this in your calculator later, or if you're studying, doing the notes, I would definitely check this in the calculator, right? Okay. And so now we've kind of figured out how to find the angle, but also how to find the dot product using this new equation that we learned, right? Okay.
No.
All right, I'm going to keep going. So parallel and orthogonal vectors. So now we know about lines. We know when lines are parallel, they're perpendicular, right? Well, in vector terms, excuse me. In vector terms, we have parallel vectors. We also have orthogonal vectors.
I can't hear you if you're speaking.
I think she lost the connection.
Okay, I'm still here. Hopefully, can you hear me? Can you guys hear me?
Yes, can hear you now.
Okay, cool.
Just
And you can probably see my screen, or you can still see my screen, right?
yeah.
Yes.
Okay. Okay, great. My computer will connect eventually and we'll deal with it as it goes. But so for perpendicular, we want to note that this is horrible. Sorry, my computer also kind of crashed, and so all these things are popping up and it's a nightmare. But for whatever reason, when
Mine
I
is the
press
same.
save-
That's why I stopped recording.
Oh,
Why
okay, I
today is
see.
like
Well,
Have
and the meetings record for me. I wonder if it's related to me recording meetings and if I should just try to not record a meeting and it would never kick me out. Because I don't even, I mean, I save the meetings, but I'm not allowed to post them and I don't even know I don't do anything with them. But okay, that's all right. So let's take a look. So we have orthogonal vectors, and these are just kind of facts about them. The cosine of the angle is 0, is 90 degrees, and the dot product is 0. This is all true. Now you can also see, like, so for parallel, then we have cosine is plus or minus 1. So cosine, if the angle is 0, it's 1. If it's 180, it's -1, right? So this is the difference. They can still be parallel, but keep in mind our theta, oh, that's not what I meant. Our theta always is in 0 to 180, right? It's from 0 to 180, including these. So these are kind of the extreme ends. So it's equal to 0 or 180 here. And then the dot product is plus or minus magnitude of V times magnitude of W, right? Because then we're multiplying by cosine of theta, which is plus or minus 1, right? Okay. So for part B here, we are determining,
I'm sorry, can you repeat that last part?
yeah, hold on. Yeah, hold on 1 second. In the background. So please, yeah. No, right. But so go or don't go to get this order. Okay. Okay. So shoot, what was the last thing I said about this?
Yes, please.
Okay.
Yeah, that.
So the dot product here, because cosine is plus or minus 1, and my equation for V dot W from the previous page is the magnitude of V times the magnitude of W times cosine of theta. So because in this case, cosine is plus or minus 1, we don't need to write that, like this piece of the equation, right? So instead we write the dot product is plus or minus the magnitudes multiplied together. We're basically just simplifying, we're simplifying this equation to just look like this in this particular case. Okay, so hopefully that makes sense, because now I can't see anybody.
Oh yeah, thank you.
Okay, cool.
That's good.
I'm like, now I can't see because I'm on my iPad, and so I can't see or hear anything. Okay.
Thanks.
All right. So for part B, and I'll try to join on my laptop, maybe, I don't know, on the next page or the next, when there's a break or something. So we're going to determine if this pair is orthogonal, parallel, or neither. And there is a way, I mean, the easiest way to do it is to figure out what the dot product is really. Like, is the dot product 0? Okay, easy. Then it's orthogonal. Is it, if it's non-zero, then, well, then you might need, if it's non-zero, you can assume that, in this case, you can assume that it's parallel. Well, but we need to get the angles. Okay, let me see, because if V dot W is non-zero, what you need to do is figure out, okay, what is cosine of theta, right? Is it plus or minus 1? Okay, but let's take a look and see what happens. So for this first one, and if cosine of theta is not plus or minus 1 or 0, right? Or the dot product's not 0, then you would have neither, right? That would be the case. So let's just take a look. This first one, I have that B is, and again, if you prefer writing these in this way, it's 2/3 -12, right? And then A, and I technically write this, it's 15 5/6, right? I don't mind it either way, but I just want to make sure you can write it in both of these ways. So if I do A dot B, right, that's always the first thing you should check, just because if it is 0, you're done. So A dot B, I get 2/3 times 15, right? Because 2/3 is my first component. Oh, maybe I'm doing B dot A, but doesn't matter. Order doesn't matter. So it's these two numbers multiplied together. Then plus 5/6, and I'm mixing up the order again, and -12. But that just goes to show even more. Order doesn't matter. It's just these two multiplied together. And then when you get this, it is, okay, so this ends up being 10. And then this is a -10. Oh, here we go. So we get 0. So this means orthogonal. Right, so that was actually part B. For whatever reason, where's part A? Oh, A was up here. Part B was, and then for part C, so we have K and S, and they gave it to us this time. So if you wanted to write this in IJ, I mean, I won't, but you could, right? So first thing we do is check the dot products, and we would say, okay, this is 1.8 times -9 plus 0.3 times 1.5, right? So I'm going to check this out. Okay, I get -16.2 minus 0.45, and then that equals -16.65. Okay, so this is not 0, so it's not orthogonal. So it's either parallel or neither, right? And so I don't know which it is, but to actually, instead of, so there, you have a few options here. You could try to figure out what is cosine of theta or what is theta. Is it 0 or 180? However, I'm realizing the easier way is to use this third equation. And we got the, so let's, here, wait, let me, oh my goodness. Let me do this. So we got the dot product, right? We figured out what, and that's on this side, and we got this. Now we can figure out what is V times magnitude of V times magnitude of W. This equals what? We can do this. And once we do that, if, oh geez, I meant the highlighter. If this equals like this up here, what we're, we're computing that, right? If this equals the same thing as what we got here, then we know they're equal and it must be parallel. And if they're not equal, then it would be neither, right? And in this case, so this is a little bit strange, but in this case, the plus and minus don't matter, right? Because keep in mind, back up here in this equation, it could be plus or minus. And whenever we do this magnitude, it's always positive. So for this question mark number, no matter what we do, because we take the square root, we're always going to get a positive number, always. But what that means is that the dot product is just negative of that, right? If it's negative, or because this guy's negative, right? So really, we're just looking to see, does this match 16.65?
Makes sense.
So,
So it can
yeah.
be positive or negative, you just need the numerical equivalence.
Right. You really just need the numerical, because if the numerical part matches up and just it's different by a sign, that just means that the angle is probably the 180, because it has this -1 affecting it. And if the sign is the same, then the angle must be 0, because then the angle is not affecting it, or the sign is not affecting it. So let's take a look and see if this is true. So it is a little bit of work. And I wrote V and W, but what I meant to write is, so maybe I'll just start this over. I meant to write K and S, right, in this case. We have K, and we want to multiply it by the S. So I'm going to solve these separately first. So magnitude of K is the square root of 1.8 squared plus 0.3 squared, right? And this is approximately, I'm getting 1.825 or 8248. And I'm not rounding this until later, kind of on purpose. But again, if you're off by like 0.2 or 0.01, I would say check that rounding, because it probably is parallel then. So then I have S, which is the square root of -9 squared plus -1.5 squared, which really is just 9 squared and 1.5 squared, right? And this should be about 9.124. And there's there's more decimal, but that's fine. So then when I go to compute this, I get, 1.8248 times 9.124, etc. And actually, I'm getting like, it's about 16.65, right? So what that means is, because these numbers match each other, right? These all are equal. That means it's got to be parallel. If they were different, it would be neither, right? So if they were different, it would be neither. And then one thing that's useful here, it says, so this question, number 5, what do we know about the angle that's between 0 and 180, or equal to, but right between this, for given the sign of VW? So they're saying, if they tell us the dot product is positive, what do we think? If they tell us the dot product is negative, what does that tell us? Now, let's look at this formula real quick. So V dot W is equal to the magnitude of V, again, times the magnitude of W, times cosine of theta. Hopefully you're sick of watching this or writing this by now. So this piece here is always positive, right? because it's magnitude. So we're taking the square root, we're squaring everything. It's always positive. Now, what that means is that this piece, this determines the sign of this right here, right? And if we look at, okay, between 0, so if this is 0 degrees, 90 degrees, 180 degrees, right? If we look at this and we think about cosine as it shifts from 0, 45, 90, like as it goes from 0 to 180, between 0 and 90, remember cosine is the x-axis, right? So it's positive here, but negative over here. So we know that cosine is positive here and it's negative there. Therefore, v dot w, if we're told it's positive, this means cosine of theta is positive. And theta is between 0 degrees and 90 degrees, right? It's in that first quadrant and it's acute, right? So then we go over to the negative side, and if VW is negative, V dot W, then that means cosine has to be negative, because that's the only way based on this equation that we can get it to be negative. And that means theta is between 90 degrees and 180 degrees. And it's also obtuse since, 90 to 180, that's basically what that means, right? So something like this, right? Okay, so I'm going to try to connect. My computer has failed me far too many times, but I'm going to try to connect back with you guys, which means I'll have to hide what I'm sharing for a sec. Okay, let me, oh no, I don't want to stop, cancel. All right, give me a moment to just. Oh, I was muted. Sorry. Of course I was talking, but I was muted. Hopefully you can all hear me now. Now I have chat back up because I could not see that before. Now you can still see my screen. Amazing. How wonderful. Except, okay, I'm on nothing, right? I'm on Zoom, so that wasn't cool. Okay, great. Back in action for the moment. So hopefully that was clear. Like if the dot product is positive and negative, we can see, or we can already know these things about cosine and about theta, right? So, okay, so that is what we're looking at here with the dot product of these vectors. Now we can also compute what we call work. And this, oh my goodness, I thought it was on the highlighter, of course. This work, typically we'll calculate it in these two fashions, right? We'll calculate either force in pounds, displacement in feet. So it's like feet pounds is the work, right? And then force in newtons or displacement in meters, work is in newtons meters, right? So this, I'm assuming like that's really what your textbook deals with. I mean, you could have probably any type of unit that you want, but these are our unit work here that we are going to use. And work in one dimension is when you're not, so when you're doing work, you're moving, something is being moved or pushed or something like that, right? That is how you're creating this work. Think of pulling, like if you're pulling, pulling something left or right? Say, and it's not moving up or down. Or say you're just taking something, whether it's, something actually heavy like moving boxes, or it's just a box of tissues. And if you are just lifting it straight up or putting it straight down, that is also work in one dimension because it's going north-south, not east-west. Or like I said, there's also crazy, I know, exercise equipment, but I'm just thinking of even when my dog doesn't want to go for a walk and I'm dragging him, pulling him, right? So I'm pulling him east-west. but he's not, unless he's jumping, he's not going up, down, right? I'm not pulling him up, down. So that would be a one dimension like work example. And the equation of work is force times displacement. And that's why notice the units are literally the unit of the force times the unit of the displacement. So that is, if that doesn't give you an indicator of the equation, yeah, I don't know what else would, right? So if you look at this number 6, how much work is done lifting a 30-pound weight straight up a distance of 4 feet? Okay, that, I mean, that sounds hard, but maybe some people can do it easily. So how much work is done? Our force is 30-pound weight. This is our force. And the distance, so the displacement is 4 feet, because we are displacing this object, this force, this distance. So think of it as vectors. You do not need to, but if you wanted to think of it as vectors, the force vector is, it's moving 0 in the x-axis, so east-west, and it's 30 pounds that you're lifting in, and the other one is 0 and 4, right? So this is the force vector, and this is the displacement vector. We do not need this, at least now or just yet, because we have this equation, right, that we're going to use. So we're going to say work is just force, which is 30 pounds, times displacement, which is 4 feet, right? So now I'm going to get, what is that, 120? So 120 foot-pounds, right? Foot time, you can put the times, but foot-pounds. So this is the work that's happening during this lifting. Now, typically, I mean, most work is in 2 dimensions, and that just means you have a component in the X and a component in the Y. So you're moving something or picking something up, and you're going east-west and north-south, right? So left, right, and up and down. And what this says, we have, if D is the displacement vector of an object, so now we're talking vectors because we're in 2D, so it's a little bit easier here. In moving the object in a straight line from points A to B under a constant force F, then the work is done by W equals F times D. I mean, that's exactly what we just did in one dimension, but this has their bold, so these are vectors. So it's actually not just multiplication, it is the dot product. And notice that I did this, I mean, on purpose a little bit. If you look at these vectors that I wrote here, if we did the dot product, like suppose I called this one F and this one D, if I did the dot product of F and D, it would be 0 times 0 plus 30 times 4. And that's exactly what we got, right? But in one dimension, we just multiply because the other component is 0. But when we're in 2 dimensions, we need to use both components. And another way, if you aren't just given the vectors, is that the work could be this equation that we already learned above, the magnitude of the force vector, the magnitude of the direction vector, and then or displacement, and then the cosine of the angle between them, right? And we just looked at this formula up above. Now we're just talking about it in terms of work. So it's representing work instead of just a scalar when we did the dot product before, right? It's actually representing work because each vector, F and D, represents force and displacement. Okay, so let's see. So a lot of kids, when I was handing out Halloween candy, doing this, or maybe adults pulling their in a wagon, which was funny. So a child pulls a wagon horizontal distance of 30 feet by pulling on the handle of the wagon with a force of this. F is 10-2 and feet pounds. Find the work done. Okay. So what we have here is, well, and notice that, I guess we'll note this equation will be used if you have the vectors explicitly. Like just they say like, oh, here's the work or force vector, here's the distance. Otherwise, you'll use this one most of the time. So this will be used, here we go. Used if you know magnitudes and the angle between our two vectors. Okay, so let's take a look at, and maybe I'm gonna do a sad little drawing of like a wagon. I'm gonna draw this picture just because I think it does help us see. So okay, here's our little here's our little wagon, right? And here's the little handle. Okay, so there's our wagon, right? And okay, I'm not going to go into a child pulling, but we won't draw that. But the force is going this way from the child pulling, and the force is 10 to the component, right? Now the displacement, they do give us this distance of 30 feet. So the displacement, and do they say direction? Yeah, it's being pulled horizontal. So that means displacement is this way, horizontal. He's only pulling, like he's not pulling up or down or back, right? And it's 30 feet. So horizontally, that means 0 in the, that's the, sorry. That means horizontal is now X, or the first component, right? I have to think north, south, east, west, not really X and Y. So the first component's 30, the second component is 0, right? So now we actually explicitly have, so we are going to use, this first formula because we explicitly have our two vectors here. So our work is going to be F times D. And that's going to be, these two multiplied together. And that means it's 10 times 30 plus 2 times 0. And that's going to be 300. And it was feet pounds, they said? Yeah, feet pounds. Okay, so that's how much work the little child is using to pull their wagon of Halloween candy. I don't know, that's what I'm picturing. Okay, this next question says we have a force of 16 pounds. So force is 16 pounds. And it's used to pull up a block. So they drew a picture for us, which is really nice because I don't have to draw my little wagon, right? And it says if the ramp is inclined 18 degrees above the horizontal, before 30 degrees above the ramp, find the work done moving the block 15 feet along the ramp. Okay, we're going to label some things because there's a lot happening, right? So we know that if we have, let's see, if we have our force, we'll start with what we know. So the force is the first thing, and it's being pulled up the ramp. So this is our force. We were told that it's 16 pounds. So that means the magnitude of the force is 16. Okay. Then we were told, okay, this angle is 30 degrees. Cool. But then we were told this dotted line here is representing displacement, because the displacement is where it's being pulled, and it's being pulled along this ramp, right? Like straight along the ramp. And so they actually even told us what they say about the displacement. It's moving the block 15 feet along the ramp. So the magnitude of this is 15. So this was 16 pounds, right? And this is 15 feet. Okay, we don't need the labels, but this is what it is. And so notice, okay, typically I see these two things. So right away, I'm thinking this equation right here, because I see these two things, right? I'm thinking that equation, which means I need theta between F and D, which means I need this 30 degrees. This is going to be my theta. And this doesn't matter. Not needed. Not needed. doesn't matter slash not needed. Because the ring is there, like there's, and it's just like, if this was being pulled along like a floor, it would be the same thing. Our floor is just tilted up, right? So it's not changing or affecting anything with the work that is being done. Maybe it's feeling like it's more difficult. Oh, right. But okay. So now we're going to say our work is going to equal, we're going to use this formula where it's the magnitude of F times the magnitude of D times the cosine of theta, right? So we know this was 16, this is 15, and this is 30. So we can actually get an exact answer here again, which is pretty cool. So W is 16 times 15, cosine of 30 degrees. And cosine of 30, is that root 3 over 2? It's root 3 over 2, I believe. Yeah. And of course, it's the more complicated one, but that's okay. So this is going to be 240 times root 3 over 2, which we can simplify, 240 divided by 2. So it's going to be 120 times the square root of 3. And what was my, okay, work, remember my label here, we were in feet and pounds, feet, foot and pounds, feet, pounds, foot, pounds, I don't know. And so this is my work for pulling, what was this, just a block? Yeah, pulling a block. Now, okay, I'm realizing we're at the end here, but there are 2 homework problems that I want to go over, but I'm wondering if I should just wait until next week because like they're homework problems. So maybe I'll let you figure them out first. But so we can, if you want to remind me, there are 2 homework problems that from 8.4 and 8.5, and maybe I'll make a note. Or okay, I'll say homework problem from 8.4 and 8.5 to be done. Oh my God, is today Thursday? Oh wow, next Tuesday. Okay, so what we are going to do, and to lay this out, right, there is a test next Thursday. So I will do homework problems, the ones specifically that I'm thinking of, because it will help you for the test. And these 2 specific problems, I don't remember if they were just more difficult or if I thought they were test related, but either way, I'd want to go through them with you because I took a note of this. So I'm going to go through those with you. Then I will also review next Tuesday. And I think, so I'll have to double check. I think I made the book problem review available tonight. And I know that the other review that's like problems that I make up that are really similar to the test, that I'm posting like at midnight. So really tomorrow, right? Because I think the book review is more important for you to get ASAP. And then that review, I'm going to go through it on Tuesday. So I'd like to take a look beforehand, do this. If you're like, I'll see it in class, and if I have questions, I can figure it out, then you do not need to go through that review until Tuesday when we're together, right? But I definitely recommend looking through the book problem. And remember, a lot of those problems are harder than what you'll see on the exam. However, when you're on the exam, you're not able to, just refer to all your notes and do all of these things, right? It's a little bit more stressful. So they might still seem difficult. So I think, like Michael said too, he said it was really helpful doing the book problems last time for that exam. So perhaps this will help for this exam too, right? Never hurt. Now, one other thing about
the same number. I'm just curious. I guess you said it's posted already?
Oh, did the test?
The book problems for this.
Oh, did I not?
Did you say it's already posted?
It should. So I'm gonna go in and I'll double check, but I thought I made it available like at the beginning of class today. But it may be that I did it after class. So I'm not entirely sure. Let me let me send a code to my phone and check.
Yeah, it's there. I was just wondering if it was
Oh,
the
it
same
is? Okay.
number. I did. I don't think I did them all. I think I did like several.
No, and
public
it's not,
section,
yeah, it's not necessary, right? There's a lot of questions
but
there,
it
but I
was very
think doing the
helpful.
ones around and doing the ones that you think would be useful or that look similar to what we do in class or look similar to
Mhm.
what you've seen on homework, like I think it's just really useful, right?
Yeah.
Okay, cool. So it is posted. However, let me check when so and the unit 4 notes, like the next unit, I will make it available next Thursday as always, but for test 3, yes, it's there. Okay, so thank you, Veronica. So for test 3, the book review problems are there. So tonight, like I said, at midnight, the test 3 review that I will do in class next week is going to be posted as well. So you do have tomorrow and the weekend and Monday to take a look at that if you want. Otherwise, what I wanted to say was I will post these notes tonight and I'll also go through those extra homework problems on Tuesday because I just think they're helpful. And I think I didn't put it in the review. Like there's a work problem on the test, right? And in the review that I made, I didn't add a work problem because they're hard to come up with without like totally, I don't know, duplicating, or maybe I was being lazy. So I saved, or let's really hope that's saved. Okay, good. So that is saved. I will post that tonight. Now in terms of the quiz, I have not posted, I don't believe I posted the answers yet. I will. And I also want to we have some time now. So I want to go through it. Let's see. Wait, you guys had a quiz, last week, right? When was your
Yes,
quiz? Was it due, or it was due this
week? It was over 4.4 and 4.5 or something.
Okay, so it's a bit old, but I'm pretty sure it's still on the test, right? So I'm gonna post the key, but let me just pull it up for you guys and you can like see it. It was quiz 4, right? Yeah, okay, here we go. So I'm gonna go through it. It was on logs. So we're going back to which maybe is good, maybe isn't. So it was on logs and I want to, okay. And I just want to talk through it. And if there's questions or people want to see anything, let me know. Book problems for this class, they're not due.
No.
So were you asking? There's no book problems that are due for this class. There's no, the homework though is due, oh yeah. Yes, Sam. Oh, I'm so sorry. Maybe this is my bad. Yes, Sam, that is perfectly fine. Don't worry about it. It's okay. And so, yeah, I should have like taken out, I could write it somewhere else. Let's see. Maybe I'll write it here. So ignore this for a second. So somebody was asking, yeah, thank you. Oh yeah. So a few people are asking yes so Peyton, I've already pulled it up. I'm sorry. I really should have changed it probably, but yeah, I won't post the quiz. I'll make it post tomorrow, but there's 1 or 2 people that are actually turning it in today because they were sick or out of town. So yes, please go ahead and leave. I will wait till you are gone. So thank you. But I want to answer the Alex homework. I do think I made it due next Tuesday. Is that right? Does it, anyone can, yeah. Okay. Michael's coming.
Yeah, before like at 6, I think.
Or it's due before class, right at the start of class. But for 5, it's not due till Tuesday. So you also have that time. If there's any objections to this, totally email me because we're just reviewing. I don't mind if it's due that, but hopefully you can get it done by Tuesday, right? And yeah, Peyton, you're good with the question of the day. Don't worry about it. Thank you though. Okay, so I'll just wait until these 2 people head out. And then this was my bad. I did this in my other class, but I didn't. Yeah, thank you, Peyton. But I didn't go over the quiz. I actually am just going to wait because they're about a week behind you guys. So they don't test till the following week. So I was like, I can go over the quiz next week, even though they just took it. Right. But a lot of people ask, like, they want the answers right away, Okay. So if I am messing this up, and this happens and someone gets it all perfect, and it's obvious, I will most likely change the quiz and send it back, but let's take a look. So it's just on logs, like most people did a pretty good job. Oh, I didn't box. I tried to like circle. So for some of these, I accepted multiple answers, which is maybe, oh, and I totally messed this up. Like I shouldn't have circled all of this, right? So for these, it's just log problems. This was expanding, and I, wanted you to expand as much as possible, and that was it, right? And then this one here, I would have accepted any, like some people left the 1/2, some people did this. Any of these were fine. So if you think you had something like this and I marked it wrong, let me know. But otherwise, this was just expanding the logs, right? Then number 2 was condensing the logs. So all I had was, write it as 1, get XY over 5 for the first one, and again, here, if you wrote like X to the 1/2, that's perfectly fine. I didn't it doesn't matter to me. That was okay. And then Y squared over 18. And then the last one was just ln. So remember, this 10 comes in, this 3 comes in, and there, oh, I messed this up actually, right? I was probably writing this way too quickly. So the Y should be in the bottom, and hopefully I graded that correctly. So, I mean, if you had Y in the top and I didn't mark it wrong, that's good for you. But it should be 42Y cubed down here. Yeah, my bad. But hopefully I did grade. If you had this and for whatever reason, I was using this key and I had written it quickly and I marked and you had exactly this, just send me a message because I can go, I mean, they're all saved what you uploaded, right? So I can just go back in and look at it and correct it, right? And then the last page was some calculator stuff. So you could have used ln, but right, I mean, most people did do log actually, but you get the same answer. So you get these decimals. And for number 4, the biggest mistakes I saw probably, or like some of them, I mean, on this page at least, were in number 4. So knowing that in this case, you had to have x minus 12 all in the parenthesis or in the exponent here. But in part B, the -4 is separate from, right? Okay, it's not times, but it's not in the exponent, right? So I can show that if there's a question about this, but otherwise, I just wanted to go through this for you guys and make sure that everybody is okay with it. Okay. Yeah, if there's no objections or questions, then great. But I will post it, and I won't post it till tomorrow due to the fact that some people did. I forgot they were going to turn it in. Well, I thought it was before class today, but I guess it was right after. So, or by midnight probably. So I'll have it posted, tomorrow at some point. And if you still have questions about this, I do recommend on Tuesday next week, we will, I can most likely take questions. Because I'm going to, unless, I mean, depends on that review, how long it takes, but I'm going to do that review, a few extra homework problems, and I'll try to pace it so that I do have time at the end of class for questions. And I will my office hours Tuesday, but Thursday I will not be doing office hours because I'll just start, I'll just start the test, right? When we take the test.
Are we doing the, there's a question, but are we going to be reviewing section 2.2 circles on Tuesday?
Oh my God, I completely forgot about that. So I'll take a look. Actually, okay. Well, let's look at this now because what I probably have it in the note. Did I post? I posted it, right? So
yeah, I think so.
Oh,
yes.
Unit 3. Yeah. Oh, here. Yep.
Mm-hmm.
Okay, so again, this is not on the test. So right. If I decide, it may just be relevant later, or it definitely would be, I mean, probably in calculus or something. So if I decide there's time and it's not going to be too confusing, maybe I would end class with this, because I know last time we did the same thing where I reviewed something and then we reviewed for the test, but I'm thinking that maybe if people want these notes, I can definitely like post it if I don't go over it.
Right.
But I'm thinking it's a no for now. But if we have time, that like if for some reason, if we have an hour left of class after reviewing, then yeah, I would definitely do it because it won't take that long. But thank you for
Okay.
bringing that up. I'll have to look
Yeah,
at that
just
over the
wanted
weekend.
to-
Yeah.
thought it
And then
was-
there's a question, you're right. Is there an exponential equation model problem on the test? Yeah, let me check real quick because I don't know and I should give you a fair, good answer. Oh, I messed this up. This should be test 3, right?
Yeah.
Yeah. I think it's-
There's going to be like harmonic motion and that kind of thing. Right?
Yeah, I think so. I do think so. So there's definitely log stuff, exponential stuff. There's that compound interest, right? But you're going to be given the equations, so you don't have to work equations. Oh, my computer's freezing. There's more log stuff. Let's see. There's law of sines and law of cosines. There's also, what was this? Not exponential. So there's some application problems that we've done, but that mostly involved like law of sines and law of cosines. It's a little tough. Okay, yeah. There's the dot product, like the vector stuff. Let's see, force and work stuff, that like the work we just did. And then there is a bearings. So there's going to be a bearings problem, like getting the true speed in the bearing. Yeah, thanks, William. Yeah, it is a lot of different subjects, but I will say there are no exponential equation models. So whichever that was, maybe we just took it out for the test because it was a lot like more difficult. I don't know. But I'll, in the review that you see, definitely bring these questions to me Tuesday. Because for the weekend, I'm going to look at it more and just double check that it's good or triple, quadruple check that it's good and that I provide you with, enough information and practice. But yeah, that for now, I believe that's all. Oh, I didn't have a question of the day for today, which is pretty bad. I think it's like the first day I haven't done it, but maybe I'll try to just think of a good one for Tuesday. I mean, I could think, I could think of something, but everything I think of lately makes me think too much. And then I say, is that really a good question? But maybe I'll get you with a thinker on Tuesday. But yeah, so I can see who's here and how long you're here for. Like the record is there, right? I mostly just like to read through and then reading your names for whatever reason, reading your names with a chat. It's kind of like seeing you in class or seeing your camera, right? Like seeing you. So it just also helps me, like get to know you, I guess is the best way virtually, right? Yeah. See, there you go. If you type in the chat, feel free to type something if you want. I think we just finished our Halloween candy today. That was left over, but mostly because I brought a bag into my in-person class, but it was I gave them all the little mini Three Musketeers that were, for whatever reason, nobody likes those. I can't remember I don't think anybody listed that in their favorite candy when I asked. So that makes sense.
Yeah. Maybe what's your least favorite?
Right. Oh, I know. Hey, all right, there we go. For tonight, if there's a least favorite Halloween candy that maybe as a kid you did not like to get or you won't give out. My sister went all out this year and she didn't get any trick-or-treaters. She was so upset and she bought push pops. She was giving out push pops.
Wow.
And like she got good candy and I think like Airheads or just random. And I thought, I said, I just bought whatever the mix was in the bag. Oh, you don't like Snickers. So we had a lot of those left too, McKenna. But push pops, I was like, man, that's a good one.
That is good. I don't really like Whoppers very much.
Cold.
That's my least favorite.
Okay. Yeah, that's all right. We'll take it. Whopper. Oh, see, I love those. Yeah. For whatever reason. Yeah.
I don't know. It's a love-hate thing. I don't know.
I think it's a childhood thing for me.
Yeah, it's very nostalgic.
Yeah, it's nostalgic. Exactly. Oh, I should just stop. interesting. But okay, so I mean, you guys, because okay, we're giving our least favorites now. If those of you that want to, yeah, no peppermint patty is okay. But yeah, you guys are free to go because class is done, and I'll end it in just a few minutes. But yeah, if there are any questions for me or anything like that, let me know, and I will definitely post the notes and then that quiz later.
Yeah. We had 2 people come by last year, and so this year we didn't do any. I didn't do it.
Wow. Okay, so
My
you
son
didn't
who's
have a
15 went trick or treating.
Okay, so he brought home all the candy for you. Yeah.
Oh yeah, like a lot. They went to a quote unquote like rich neighborhood where they
Of
gave
course,
up
isn't
full
that what the kids
size.
do? Yeah,
You know,
I
they
just
gave up
hope